Before the birth of the first star, the universe was a vastly different place, an expanse of gas, radiation, and cosmic dust. This era, known as the cosmic dark ages, is shrouded in mystery. For over 13 billion years, the universe existed in a state of near darkness, with no stars to light the sky or galaxies to shape the cosmic landscape. Yet, as we dig deeper into the mysteries of the universe's early moments, we are uncovering an extraordinary secret, one that challenges everything we thought we knew about the cosmos. What happened in the universe before the first star? And why has this crucial period been hiding in the shadows of cosmic history for so long? The story of the universe's earliest years begins shortly after the Big Bang. In the beginning, the universe was a hot, dense soup of particles, protons, neutrons, electrons, and photons, all colliding and interacting in a chaotic dance. As the universe began to cool and expand, these particles started to form simple atoms, mostly hydrogen and helium, marking the first step in the formation of the cosmos as we know it. However, despite the fact that atoms had formed, the universe remained opaque, as light was scattered by free electrons, preventing photons from traveling freely. This opaque state of the universe lasted for hundreds of thousands of years, a period referred to as the recombination era. It was only after this period, when the universe cooled sufficiently for electrons and protons to combine into neutral atoms, that the universe began to transition from a dense fog to the transparent space we observe today. However, even after this shift, the universe remained relatively dark. No stars had yet ignited to light the skies. This era, which spanned millions of years, is known as the cosmic dark ages. The cosmic dark ages were a time of profound silence and stillness, where only the faint glow of the afterglow of the Big Bang, known as the cosmic microwave background radiation, CMB, permeated the cosmos. This radiation, a remnant of the Big Bang itself, provided the only illumination in a universe otherwise devoid of light. But during this time, something extraordinary was happening beneath the surface, something that has only recently begun to come into focus. The first whispers of structure were beginning to form. While the universe was still dark and silent, the gas and dust scattered across space began to clump together under the influence of gravity. These small fluctuations in density marked the beginning of the formation of the first galaxies, and more importantly, the formation of the very first stars. But these stars didn't appear overnight. It took hundreds of millions of years for enough matter to accumulate and for the conditions to become right for the first stars to ignite. These first stars, known as population 3 stars, were born from the primordial gas of hydrogen and helium, elements created during the Big Bang without any heavier elements that we are familiar with today. The strange secret that the universe has been hiding for so long is that, while the first stars were eventually born, their creation wasn't a simple, straightforward process. The birth of these stars marked a monumental shift in the universe, igniting the first sources of light and heat and transforming the cosmos into a dynamic, ever-evolving entity. But before these stars could form, there was a period of cosmic evolution that scientists have only recently begun to understand. What exactly happened in the universe during these dark ages? How did the transition from a completely dark universe to one filled with stars and galaxies occur? New discoveries are pointing to the fact that the conditions required for the birth of the first stars were not as straightforward as we once thought. In fact, they may have been influenced by a strange phenomenon, one that could hold the key to understanding the very origins of cosmic structure. This phenomenon is thought to be the presence of cosmic seeds, tiny fluctuations in the density of matter during the early universe. These tiny fluctuations acted as the seeds for the formation of the first stars and galaxies, but they were far more intricate than previously believed. They were not simply random fluctuations in matter, but rather the result of underlying forces that shaped the way the first stars and galaxies formed. These cosmic seeds may have been influenced by a number of factors, including the presence of dark matter, a mysterious substance that has never been directly observed, but is thought to make up the majority of the universe's mass. Dark matter, which does not emit light or interact with electromagnetic radiation, is detectable only through its gravitational effects on visible matter. It is believed to have played a crucial role in the formation of the first structures in the universe, acting as the gravitational scaffolding that allowed matter to clump together and form the first galaxies. But recent findings suggest that dark matter may have also played a more direct role in the creation of the first stars, potentially providing the necessary gravitational pull to ignite the process of stellar formation. One of the most intriguing aspects of this discovery is that these early cosmic fluctuations, driven by dark matter and other hidden forces, may have caused the universe to undergo a rapid transformation, one that led to the sudden emergence of the first stars. These first stars, which were unlike anything we see today, may have been massive and short-lived, burning through their fuel in a fraction of the time it takes for modern stars to burn through theirs. They were likely the ancestors of the more familiar stars that followed, and their birth marked the beginning of the universe's journey from darkness to light. As scientists continue to study the cosmic dark ages, they are uncovering more details about how the first stars were born and what role dark matter played in this process. Through advanced simulations, powerful telescopes, and the study of ancient cosmic light, researchers are beginning to piece together the story of the first stars, stars that were not made of the elements we are familiar with, but instead were composed of the very building blocks of the universe itself. These early stars played a crucial role in the evolution of the cosmos, enriching the universe with the first heavy elements and setting the stage for the formation of galaxies, planets, and eventually life. But the secrets of the universe before the first star don't end there. The cosmic dark ages may also hold the key to understanding the true nature of the universe's expansion. For years, scientists have debated the question of whether the universe's expansion is a one-way journey, or whether it will eventually reverse. The birth of the first stars may have been the catalyst that changed the course of cosmic evolution, setting the universe on a path toward the vast, complex cosmos we observe today. But the events that led to the formation of these stars are still shrouded in mystery, and there are many unanswered questions about the true nature of the universe's early moments. The strange secret that the universe has been hiding is not just about the birth of the first stars. It is about the forces that shaped the cosmos in its earliest stages. These forces, dark matter, cosmic fluctuations, and the birth of the first stars, formed the foundation of the universe as we know it. But as scientists dig deeper into the early history of the universe, they are uncovering more about the origins of the stars, galaxies, and cosmic structures that shape the universe today. The universe before the first star is not just a dark, silent void. It is a pivotal moment in cosmic history, one that shaped the universe into the complex and dynamic system that we observe today. As we continue to study this hidden period in the universe's history, we will likely uncover even more secrets about the forces that drove the birth of stars, galaxies, and all the elements that make up the cosmos. The strange secret the universe has been hiding may be one of the most profound revelations in the history of cosmology, and it may ultimately unlock the key to understanding the origins of the universe and the forces that continue to shape its evolution. As we delve deeper into the epoch before the birth of the first stars, we begin to uncover the events that set the stage for one of the most significant transformations in the universe's history. The period known as the Cosmic Dark Ages remains one of the most mysterious and enigmatic chapters in the cosmic timeline. While stars, galaxies, and other celestial bodies dominate our view of the universe today, this dark era was marked by the absence of any luminous objects, leaving the cosmos in a state of obscurity. What occurred during this time, and how did the conditions of the universe lead to the eventual formation of the very first stars? The universe's early moments were dominated by a chaotic mix of primordial matter. Following the Big Bang, the universe was incredibly hot and dense, with a soup of particles that had yet to form into the atoms we are familiar with today. It was during this phase that the first atoms, mostly hydrogen and helium, began to form, cooling as the universe expanded. However, even with the formation of atoms, the universe remained opaque to light. The photons, the particles of light, were unable to travel freely because they were constantly scattered by the abundant free electrons that filled space. This photon scattering kept the universe in a state of fog, unable to reflect the clarity we associate with the visible cosmos today. This state of opacity lasted for hundreds of thousands of years until a dramatic shift occurred. The universe cooled to a point where electrons could combine with protons to form neutral hydrogen atoms, a process known as recombination. This was a pivotal moment as it allowed photons to travel freely through space for the first time. The universe transitioned from being opaque to transparent, allowing light to spread throughout the cosmos. This moment, known as the decoupling of matter and radiation, was key to setting the stage for what would follow. However, despite the transition to transparency, the universe was far from the vibrant starry landscape we observe today. While photons could now travel freely through space, the universe was still devoid of the luminous objects that we now associate with cosmic evolution. The period of transparency marked the universe's shift into the cosmic dark ages, a time before the formation of stars, galaxies, and the more familiar structures we associate with space. During this era, the universe was composed mostly of hydrogen and helium gas, with only faint traces of radiation from the Big Bang. But while the universe was in this state of relative darkness, something remarkable was already beginning to happen. The hydrogen and helium gas that filled space began to undergo small fluctuations in density. These slight variations, while seemingly insignificant, were actually the seeds for the future formation of galaxies, stars, and other cosmic structures. These fluctuations in density, created by the interplay of gravitational forces, allowed small pockets of matter to clump together over time, gradually forming the first structures in the universe. It's important to note that the process of star formation didn't happen instantaneously. The gas was still predominantly composed of hydrogen and helium, and it took hundreds of millions of years for these gas clouds to collapse under gravity's influence and form the first stars. These early stars, known as population 3 stars, were unlike any stars we see today. They were incredibly massive and hot, burning through their fuel at an astonishing rate. Their birth marked the beginning of the end of the cosmic dark ages and the onset of a new era in the universe's evolution. But what exactly caused these fluctuations in density? What was responsible for the formation of these seeds of galactic and stellar birth? The answer lies in one of the universe's most elusive and mysterious components: dark matter. While dark matter cannot be seen directly, its presence is inferred from its gravitational effects on visible matter. It is believed that dark matter played a crucial role in the formation of the first cosmic structures, including galaxies and stars. In the earliest stages of the universe, dark matter's gravitational pull acted as the scaffolding that helped to shape the formation of gas clouds. These dark matter halos provided the necessary gravitational pull to draw gas together, eventually leading to the formation of the first galaxies and stars. The presence of dark matter in these early stages of the universe is essential for understanding the birth of cosmic structures, and without it, the formation of the first stars may not have been possible. Yet, despite the crucial role dark matter played, the true nature of this elusive substance remains a mystery. We know that dark matter doesn't interact with light or electromagnetic radiation, which is why it is invisible to our telescopes. But its presence is felt through its gravitational influence on visible matter. This means that, although we cannot directly observe dark matter, we can see its effects by looking at the motion of galaxies and galaxy clusters. By studying how dark matter interacts with visible matter, scientists are beginning to piece together the story of how it helped shape the early universe. Another key factor in the early universe's evolution is the role of radiation. As the universe expanded and cooled, the temperature dropped, and the energy from the Big Bang began to dissipate. This radiation, known as the cosmic microwave background, CMB, is the faint glow left over from the Big Bang. While this radiation is no longer capable of illuminating the universe, it remains a vital tool for understanding the early universe. By studying the CMB, scientists can learn about the conditions of the universe before the first stars formed. The CMB offers a snapshot of the universe just 380,000 years after the Big Bang, providing us with a direct link to the cosmic dark ages. But even as radiation and dark matter played their roles in the formation of the first stars, there is still much we don't understand about this period of cosmic history. What exact mechanisms allowed the gas clouds to collapse into stars? How did the first stars manage to ignite, given that they were composed solely of hydrogen and helium with no heavier elements to catalyze nuclear fusion? And what role did dark matter play in providing the necessary trigger for these processes? These are questions that continue to drive research into the early universe. While scientists have made tremendous progress in understanding the birth of the first stars, many mysteries remain. One of the most exciting possibilities is that future advancements in observational technology, such as next-generation space telescopes and advanced computer simulations, will allow us to peer even deeper into the universe's earliest moments. By studying the faint traces of radiation, gravitational waves, and other cosmic phenomena, scientists hope to uncover even more about the period before the first star, an era that has remained largely hidden from our view for billions of years. But the significance of this period goes beyond just the formation of stars. The transition from the cosmic dark ages to the age of stars was a pivotal moment in the history of the universe. The birth of the first stars did not just light up the universe, it set in motion a cascade of events that would lead to the formation of galaxies, black holes, planets, and eventually, life itself. Without these early stars, the universe as we know it would not have existed. As we continue to explore the universe's early moments, it becomes increasingly clear that the cosmic dark ages are not just a period of emptiness and darkness. They are the foundation of everything we know, everything from the formation of galaxies to the creation of life on Earth. The strange secret the universe has been hiding is that this period before the first star, is far more significant than we ever realized. It is the key to understanding how the universe evolved, how galaxies formed, and how life in its many forms came to exist in the vast expanse of space. As we continue our journey through the early moments of the universe, we encounter a critical shift that forever changed the course of cosmic history: the birth of the first stars. These stars, often referred to as population 3 stars, were unlike anything we see today. They were formed from the primordial gas of hydrogen and helium, the very elements that were created during the Big Bang. Without the presence of heavier elements like carbon, oxygen, or iron, these first stars were incredibly massive, burning hot and fast, living only a short, explosive existence. Their birth marked the end of the cosmic dark ages and the beginning of a new era, one where light, heat, and complexity would begin to fill the universe. But what exactly triggered the formation of these first stars? The process was not instantaneous. It took hundreds of millions of years after the Big Bang for the necessary conditions to align, but the moment they did, the universe would never be the same. The gas clouds that filled space began to collapse under the influence of gravity. This collapse wasn't a simple process. It required precise conditions. For the gas to collapse efficiently enough to form a star, it needed to be dense and cool enough to allow particles to come together. But the most crucial factor was the role of dark matter. The dark matter halos surrounding these gas clouds provided the gravitational pull necessary to overcome the pressure from the gas and initiate the collapse. The gravitational pull of dark matter was the invisible hand guiding the formation of stars, galaxies, and other cosmic structures. As dark matter clumped together in dense pockets, it created gravitational wells that drew in the hydrogen and helium gas. This process of gravitational collapse eventually led to the formation of the first stars. These stars, in turn, ignited the beginning of cosmic history as we know it, as they provided the first sources of light, heat, and radiation that would give rise to galaxies, black holes, and the building blocks for future generations of stars and planets. But what was life like for these first stars? These early stars were colossal, many times the mass of our Sun, and they burned through their nuclear fuel at an astonishing rate. They were made primarily of hydrogen and helium, with no heavier elements like metals to act as a cooling agent in their cores. As a result, their temperatures reached staggering heights, millions of degrees hotter than our Sun. This extreme heat caused them to burn rapidly, exhausting their fuel in just a few million years, a short lifespan compared to the billions of years that stars like our Sun endure. Despite their short lives, the first stars played a pivotal role in shaping the universe, as they were the first objects to begin the process of cosmic enrichment, producing the elements that would later form planets, life, and the complex structures we see today. One of the most important contributions of these first stars was the creation of heavy elements such as carbon, oxygen, and nitrogen, elements essential for life as we know it. These stars were the first cosmic furnaces, fusing hydrogen and helium into these heavier elements through the process of nuclear fusion. When these stars reached the end of their short lives, they exploded in supernovae, scattering the elements they had created throughout the universe. This stellar death and the subsequent release of elements were the foundation for the formation of the next generation of stars, planets, and galaxies. Without the death of these early stars, the universe would have remained a barren expanse of hydrogen and helium, unable to support life. The death of these first stars also marked the beginning of another cosmic process, the formation of black holes. Some of these early stars were so massive that, when they collapsed, they created black holes, regions of space where gravity is so intense that not even light can escape. These black holes were the precursors to the supermassive black holes found at the centers of most galaxies today. They acted as cosmic anchors, helping to shape the growth of galaxies and influencing the development of cosmic structures on a grand scale. The formation of these black holes also set the stage for the formation of quasar-like objects, bright active centers of galaxies powered by the accretion of matter around these supermassive black holes. But while these early stars and their explosions created the elements necessary for life, the universe wasn't entirely hospitable to life at this point. The radiation released by these stars and the subsequent supernovae blasts would have been too intense for life to form in any meaningful way. The environment was hostile, highly energetic, chaotic, and devoid of the stable, quiet conditions needed for the emergence of life. Still, the seeds were being planted. The elements forged in the cores of the first stars would eventually lead to the formation of planets, and the cosmic processes that began with the death of these stars would later allow life to emerge in the universe. The birth of the first stars also marked the beginning of the process that would eventually lead to the formation of galaxies. As stars began to form in dense clusters, they gave rise to early galaxies. These early galaxies were much smaller and more irregular than the large spiral galaxies we are familiar with today. They were often chaotic and violent, filled with intense radiation, supernovae, and black holes. But they were the building blocks of the galaxy clusters we see today, with the same dark matter and gravitational forces that shaped the first stars continuing to govern the growth of galaxies. This early period of cosmic history, while marked by chaos and violence, was the foundation for the universe we know today. The first stars, though short-lived, were the progenitors of everything that followed: galaxies, stars, planets, and, eventually, life. But what was it about this period that made the first stars so unique? What were the forces at play that allowed the universe to transition from a hot, dense, and chaotic state to one that could support the creation of stars, galaxies, and life? The answer lies in the delicate balance of forces that existed in the early universe. The key to understanding the formation of the first stars is the interplay between gravity, gas, and dark matter. Dark matter, which we cannot directly observe but can infer from its gravitational effects, acted as the invisible scaffolding around which ordinary matter could come together to form the first stars. The gravitational pull of dark matter allowed gas clouds to collapse and form the first stellar nurseries, setting the stage for the birth of light and heat in the universe. The role of dark matter in this process is significant, as it helped to shape the formation of galaxies and stars. Without the presence of dark matter, the gas clouds in the early universe may not have had enough gravitational pull to collapse and form stars. The universe would have remained a dark, sterile place, devoid of the energy and complexity needed for life to arise. The presence of dark matter made it possible for the first stars to form, and their birth set in motion the processes that would eventually lead to the creation of galaxies, planets, and the conditions for life. As we continue to study the early moments of the universe, we are gaining new insights into the processes that led to the formation of the first stars. With advanced telescopes, sophisticated simulations, and cutting-edge observational techniques, scientists are uncovering the hidden secrets of the early universe, peering into the cosmic dark ages to understand how the universe went from a dark, chaotic place to the vast, star-filled expanse we see today. The birth of the first stars was the turning point in the history of the universe, and the more we learn about this period, the closer we come to understanding the ultimate origins of everything in the cosmos. As we continue to explore the origins of the first stars, we begin to uncover a deeper understanding of the forces that shaped not only their birth but the entire cosmic landscape. The creation of the first stars was not an isolated event. Rather, it was the starting point of an extraordinary transformation, a process that laid the foundation for the formation of galaxies, the synthesis of complex elements, and the eventual development of life itself. But what exactly enabled the first stars to form in the first place? What were the conditions and processes at play in the early universe that made these first stars possible, and how did they ultimately shape the cosmos? One of the key factors in the formation of the first stars was the presence of primordial gas, composed primarily of hydrogen and helium. These elements, created in the aftermath of the Big Bang, were the building blocks of the universe. However, while hydrogen and helium were the most abundant elements, they were not enough on their own to trigger the formation of stars. For stars to form, the gas needed to be compressed into dense clouds under the force of gravity, and this is where dark matter played a crucial role. Dark matter, an invisible substance that makes up a significant portion of the universe's mass, exerted a gravitational pull on the surrounding gas. It is important to note that while we cannot directly observe dark matter, its presence is inferred from its gravitational effects on visible matter. In the early universe, dark matter was distributed in large, diffuse halos that surrounded the gas clouds. The gravitational pull of dark matter in these halos created gravitational wells that helped to draw the gas together. These dense pockets of gas began to collapse under their own gravity, eventually reaching the temperatures and pressures necessary for nuclear fusion to begin. In essence, dark matter provided the scaffolding that allowed the primordial gas to condense into the first stellar bodies. But dark matter's role in star formation wasn't as straightforward as simply providing gravity. It also shaped the overall structure of the universe. As dark matter clumped together, it began to influence the distribution of ordinary matter, hydrogen and helium gas, by guiding it into dense regions where stars and galaxies could eventually form. The result was the emergence of the first cosmic structures, from small proto-galaxies to isolated stars. Dark matter helped to give the universe its framework, laying the foundation for the galaxies that would later fill the cosmic landscape. But what happened when the first stars ignited? These stars, unlike the ones we see today, were massive and short-lived. They were made primarily of hydrogen and helium, with no heavier elements like carbon or oxygen to facilitate cooling. As a result, the first stars burned incredibly hot and fast, exhausting their nuclear fuel within just a few million years, a far shorter lifespan than our Sun, which will last for billions of years. These early stars were titanic in size, many times the mass of the Sun, and they were capable of burning through their fuel at an incredible rate. This short life cycle, however, had enormous consequences for the evolution of the universe. The death of these first stars was just as dramatic as their birth. When these massive stars ran out of fuel, they exploded in violent supernovae, scattering their outer layers into the surrounding gas. This explosion was more than just a spectacular burst of light. It was a cosmic event that enriched the universe with heavier elements such as carbon, oxygen, nitrogen, and iron. These elements, which are essential for life, had never existed before the death of the first stars. Without these early supernovae, the universe would have remained a sterile place, devoid of the complex chemistry needed to form planets and, eventually, life. In addition to the enrichment of the universe with these vital elements, the death of the first stars also led to the formation of black holes. The most massive stars, when they died, collapsed under their own gravity, forming black holes, regions of space where gravity is so strong that nothing, not even light, can escape. These early black holes were the progenitors of the supermassive black holes that we find at the centers of most galaxies today. These supermassive black holes played a crucial role in the development of galaxies, influencing their shape, growth, and evolution. Their gravitational pull helped to shape the way galaxies formed and interacted, contributing to the complex interconnected structure of the universe. As we learn more about the first stars, it becomes increasingly clear that they were not just the light bulbs of the universe, they were the catalysts for everything that came afterward. The elements they produced, the black holes they left behind, and the gravitational influence they exerted shaped the evolution of galaxies, stars, and planetary systems. In essence, the first stars were the architects of the universe. Their death marked the beginning of the complex, multi-layered cosmos we might observe today. However, the process of star formation did not stop with these early massive stars. As the universe continued to evolve, the conditions for the formation of new stars began to change. The heavier elements produced by the first stars spread throughout the universe, enriching the primordial gas with the building blocks needed for the formation of more complex stars. These new stars, unlike the first ones, were composed of hydrogen, helium, and a much higher proportion of heavier elements. The formation of these second-generation stars marked the beginning of the universe as we know it, with the creation of solar systems, planets, and the eventual emergence of life. The second generation of stars was significantly different from the first. These stars were smaller, cooler, and longer-lived, and they formed from gas that had been enriched with heavier elements from the first stars. These stars were also more likely to form in regions where dark matter played a less dominant role. Instead, their formation was influenced by the complex interplay of gas, gravity, and the presence of the heavier elements that had been produced by earlier supernovae. These stars, though less massive than the first stars, had a more profound impact on the universe's evolution. Their longer lifespans allowed for more complex chemical processes to occur, and over time, the elements produced by these stars would give rise to planets, solar systems, and eventually life itself. One of the most significant outcomes of this process is the formation of habitable planets. The elements produced by the first stars made it possible for planets to form around newer stars, creating the conditions for life to arise. Without the death of the first stars and the enrichment of the universe with heavier elements, planets like Earth and life itself would never have existed. The story of the first stars is, in many ways, the story of the origins of life, as the elements necessary for life were forged in the hearts of these early cosmic giants. The birth and death of the first stars also set the stage for the development of galaxies and the large-scale structure of the universe. These stars were the building blocks of galaxies, and their gravitational influence helped to shape the evolution of cosmic structures. The first galaxies, born from the ashes of these early stars, would grow into the massive galaxy clusters we observe today. And at the center of many of these galaxies, supermassive black holes would form, playing a key role in shaping the growth and behavior of their galaxies. As we continue to study the early universe and the birth of the first stars, we are gaining valuable insights into the fundamental processes that shaped the cosmos. These stars were not just the first lights in the universe, they were the creators of everything that came afterward. From the elements necessary for life to the formation of galaxies, black holes, and solar systems, the first stars set the stage for everything we see in the universe today. As we continue to explore the early universe and the formation of the first stars, one of the most significant revelations is the pivotal role these stars played in the creation of the elements essential for life as we know it. The early universe, immediately after the Big Bang, was predominantly filled with just hydrogen and helium, light elements forged in the fire of the Big Bang. While these elements were crucial in the formation of the first stars, it was only through stellar processes that the heavier elements, the metals necessary for the building blocks of life, would come into existence. These first stars, known as population 3 stars, were the universe's first reactors, fusing hydrogen and helium in their cores to create heavier elements. The process of nuclear fusion within these stars produced a range of elements, but it was their violent deaths through supernova explosions that scattered these elements across the universe. This process, known as nucleosynthesis, was the universe's first step in the creation of complex matter. These early stars gave birth to elements like carbon, oxygen, nitrogen, and iron, the very elements that would eventually make life possible on Earth. The explosion of these early stars, which ended in supernovae, released an immense amount of energy, triggering the creation of even heavier elements like gold, silver, and uranium. These elements were scattered throughout space and would later become the foundation for the formation of planets, stars, and ultimately, life itself. The supernovae from these population 3 stars acted as the first cosmic factories, producing the essential raw materials for the creation of new galaxies, new stars, and new worlds. Without this stellar enrichment, the universe would have remained a barren and sterile place, unable to sustain life or form complex structures. But these early stars didn't just create elements, they also played a role in shaping the environment of the early universe. The first stars, due to their immense size and energy output, were capable of emitting vast amounts of radiation. This radiation had a profound effect on the surrounding gas, ionizing it and transforming the very nature of the cosmos. This process, called rionization, marked the end of the cosmic dark ages and the beginning of an era in which light would finally begin to spread across the universe. The rionization era was the universe's first major transition from a dark and opaque state to a more transparent one where light from stars could travel freely through space for the first time. Rionization was a crucial period in the universe's evolution. It not only allowed light to spread across the cosmos, but also laid the foundation for the development of galaxies. With the ionized gas now able to interact more freely with the energy from stars, the universe began to clear up, in a sense, enabling the formation of more complex cosmic structures. The first galaxies, formed from clumps of dark matter and gas, began to take shape in this newly lit universe, and these galaxies would go on to become the building blocks of larger cosmic structures. However, despite the transformative role the first stars played, we still don't fully understand how these stars were able to form in the first place. The universe's early gas was composed mostly of hydrogen and helium, with little to no heavy elements present to aid in the cooling process required for star formation. The key to understanding how these stars formed lies in the nature of the cosmic gas clouds that existed at the time. These primordial clouds, rich in hydrogen and helium, were highly unstable, and under the influence of gravity, they began to collapse. This collapse generated enough heat and pressure to trigger nuclear fusion in the hearts of these gas clouds, igniting the first stars. What is still unclear, however, is what triggered this collapse. What force or mechanism caused these gas clouds, initially spread out across the universe, to collapse into dense regions that could form stars? Some scientists speculate that it was the influence of dark matter. As dark matter clumped together, it created gravitational wells that pulled the gas clouds into them, initiating the collapse. Others believe that the process could have been influenced by radiation or cosmic shocks, perhaps from the remnants of the Big Bang or from early cosmic events that caused ripples in the surrounding gas. While we may not yet know exactly what initiated the first star formation, the role of dark matter remains a likely key factor in the process. Another question that continues to puzzle scientists is why the first stars were so massive. Population 3 stars were far larger than the stars we see today, with masses up to several hundred times that of the Sun. This difference in size and mass had important consequences for their evolution. Larger stars burn their fuel much faster than smaller stars, and as a result, they live much shorter lives, just a few million years compared to the billions of years that our Sun will endure. These massive stars lived fast and died young, exploding in supernovae that dispersed their elements throughout the universe, enriching the cosmos with the materials necessary for future star formation. The question of why the first stars were so massive is still an area of active research. Some scientists propose that the lack of heavy elements in the early universe may have played a role. Without metals like carbon, oxygen, and nitrogen to help cool the gas clouds, the gas was unable to form the smaller stars that we see today. The gas instead collapsed into massive hot stars that burned through their fuel at an extraordinary rate. These first stars were essentially the cosmic heavyweights of their time, their enormous size a direct result of the unique conditions in the early universe. In addition to their massive size, the first stars were also extremely hot. With temperatures in the millions of degrees, they burned at temperatures much higher than modern stars. This extreme heat, combined with their massive size, meant that they were capable of producing intense radiation that flooded the early universe. This radiation had a profound effect on the surrounding gas, ionizing it and initiating the process of reionization. This momentous shift allowed light to travel freely through the universe for the first time, marking the end of the cosmic dark ages and ushering in a new era of cosmic evolution. As we continue to explore the earliest moments of the universe, we are gaining new insights into the formation of the first stars and the profound impact they had on the development of the cosmos. These stars were not only the creators of the elements necessary for life, but they also played a central role in shaping the universe's structure, setting the stage for the birth of galaxies, the formation of black holes, and the eventual emergence of life on Earth. Understanding the birth and death of these early stars is crucial to understanding the evolution of the universe as a whole. But the questions raised by the formation of the first stars don't end with their creation. The supernovae that resulted from their death scattered the elements they created across the universe. But what happened next? How did the materials left behind by these early stars contribute to the formation of the galaxies and structures we observe today? What was the process by which the universe evolved from a hot, chaotic state to one filled with the intricate complexity we see in the cosmos today? These are the questions that continue to drive cosmologists and astronomers as they seek to understand the fundamental processes that shaped the universe and everything within it. As we venture deeper into the birth and death of the first stars, we begin to uncover the long-lasting effects these ancient cosmic giants had on the evolution of the universe. The explosive deaths of these stars, known as supernovae, were not just dramatic events, but marked pivotal moments in the transformation of the cosmos. These colossal explosions didn't just scatter elements into the surrounding space, they kick-started the processes that would lead to the formation of galaxies, planetary systems, and the complex structures we observe today. The heavy elements produced during the violent deaths of the first stars were vital in forming the building blocks of planets and life. Elements like carbon, oxygen, nitrogen, and iron, crucial for the creation of planets, stars, and even biological life, did not exist in the universe until these stars exploded. Their supernovae acted as cosmic factories, forging these elements in the intense heat and pressure at the core of these massive stars. When these stars died, they released the elements into the surrounding space, seeding the next generations of stars and planets with the raw materials needed for more complex structures to form. One of the key questions that has emerged from this understanding of the first stars is, how did these elements lead to the creation of planets and the subsequent formation of solar systems? The process is far more complicated than one might imagine. The death of these stars enriched the surrounding gas clouds with heavier elements, but for planets to form, Additional steps were required. Over time, the enriched gas clouds began to collapse under their own gravity, eventually forming the first galaxies. Within these galaxies, stars continued to form, each carrying with it the remnants of earlier supernovae. But it wasn't just stars that formed in these regions, planets began to emerge as well. In the dense gas clouds around young stars, dust particles began to collide and stick together, forming larger and larger bodies. This process, known as accretion, is what led to the formation of planets, moons, and asteroids. The heavier elements produced by the first stars were critical in this process. Without elements like carbon, oxygen, and iron, planets like Earth and the possibility of life would not have been possible. These elements were the building blocks for the chemical reactions that would eventually give rise to planets capable of supporting life. The supernovae of the first stars also played a critical role in shaping the development of galaxies. As the explosions scattered heavy elements throughout space, they influenced the formation of new generations of stars and galaxies. These stellar remnants acted as seeds for the next generation of cosmic structures, guiding the formation of spiral galaxies, elliptical galaxies, and galaxy clusters. The gravitational influence of these remnants, along with the dark matter that shaped the structure of the universe, helped to determine the shapes and sizes of the galaxies that would form in the wake of the first stars. But while the first stars gave birth to galaxies, planets, and elements, their death also set the stage for some of the most violent and fascinating phenomena in the universe. The remnants of the first stars, whether in the form of black holes or neutron stars, continue to shape the cosmos today. These cosmic remnants act as cosmic engines, driving the evolution of galaxies and influencing the behavior of surrounding matter. In particular, black holes, which were formed from the collapse of the most massive stars, have become central players in the evolution of galaxies. Supermassive black holes, which are believed to reside at the center of most galaxies, were likely born from the remnants of the first stars. These black holes play a crucial role in the formation and behavior of galaxies. They act as cosmic anchors, helping to shape the structure of galaxies by exerting a powerful gravitational pull. The gravitational forces of these black holes influence the orbits of stars within the galaxy and regulate the rate at which new stars form. In many ways, black holes are not just cosmic anomalies, they are essential for the growth and evolution of galaxies. In addition to supermassive black holes, the death of the first stars also led to the formation of neutron stars, which are the remnants of stars with a mass between that of a white dwarf and a black hole. Neutron stars are incredibly dense objects, with a mass greater than that of the Sun compressed into a sphere only a few kilometers across. These stars are so dense that their gravity is strong enough to warp space-time around them. Neutron stars are also the birthplaces of some of the most intense and mysterious phenomena in the universe, including gamma-ray bursts and gravitational waves. The study of these objects provides a window into the extreme conditions that govern the universe and offers insights into the fundamental laws of physics. The death of the first stars also played a crucial role in the process of reionization, a key event in the universe's evolution. During the cosmic dark ages, the universe was mostly opaque to light, as the gas was ionized and scattered photons. However, when the first stars ignited, they began to emit ultraviolet radiation that reionized the surrounding gas, allowing light to travel freely through the universe. This event, known as reionization, marked the end of the cosmic dark ages and the beginning of the universe's bright era, where light from stars and galaxies began to fill the cosmos. While the process of reionization is well understood in many respects, scientists are still unraveling the finer details of how it occurred. One of the key questions is what role the first stars played in this process. Were they the primary agents of reionization, or did other factors, such as the presence of dark matter or the formation of supermassive black holes, also contribute? Understanding how reionization occurred is crucial for our understanding of the evolution of the universe and the conditions necessary for life to emerge. The influence of the first stars extends far beyond their immediate environment. Their death and the subsequent spread of heavy elements enriched the entire universe, creating the conditions necessary for the formation of planets, galaxies, and eventually life. These first stars were the building blocks of everything we know: galaxies, stars, planets, and the very elements necessary for life. Without them, the universe would have remained a barren and sterile place. Their role in the formation of the universe was not just a cosmic coincidence, it was the result of a delicate balance of forces that guided the universe's evolution. The process that led to the formation of the first stars was a complex interplay of gas, gravity, dark matter, and radiation. The universe, in its infancy, was a chaotic and violent place, but out of this chaos, the first stars emerged, giving birth to the elements that would shape the universe and set the stage for the eventual emergence of life. These stars did not just create the universe as we know it, they set in motion the processes that led to the development of galaxies, stars, planets, and ultimately, the conditions necessary for life. As we continue to explore the early universe and the birth of the first stars, we gain new insights into the fundamental forces that shape the cosmos. The discovery of these early stars has profound implications for our understanding of the universe, from the formation of galaxies to the creation of planets and life. The first stars were not just the lights of the universe, they were the architects of everything that followed. Their birth and death were the starting points of cosmic evolution, and their legacy continues to shape the universe to this day. As we move forward in understanding the impact of the first stars, we now shift our focus to the cosmic processes that were set in motion by their formation and eventual death. These early stars were not just the first sources of light in the universe, they were the architects of the universe's chemical evolution. Their explosions, known as supernovae, played a pivotal role in the enrichment of the universe, seeding it with heavy elements and setting the stage for the formation of new stars, planets, and eventually, life. One of the most critical effects of the first stars was the creation of heavier elements through nuclear fusion. Stars are like cosmic factories, fusing lighter elements like hydrogen and helium into heavier elements in their cores. The first stars, made up of almost entirely hydrogen and helium, began the process of converting these simple elements into the more complex ones necessary for the formation of planets and life. Elements such as carbon, oxygen, and nitrogen, the building blocks of life, were produced in the cores of these early stars. However, it wasn't just the act of fusion that was important. The ultimate fate of these stars would have a far more profound impact. When the first stars exhausted their fuel, they exploded in a supernova, a cataclysmic event that released an immense amount of energy. In the core of these explosions, the conditions were so extreme that even heavier elements were forged, elements like iron, gold, and uranium. These newly created elements were then scattered across the universe by the supernova shockwaves. The explosion of the first stars essentially seeded the universe with the raw materials that would later form galaxies, planets, and the very elements necessary for life. But the role of supernovae in the cosmic evolution doesn't stop with just the creation of elements. The shockwaves from these explosions also created powerful winds that swept through the gas clouds surrounding the stars, pushing and pulling the gas into new shapes. These winds from supernovae acted as a kind of cosmic bulldozer, influencing the formation of new stars and galaxies. The violent shock waves would have compressed gas in certain regions, triggering new rounds of star formation. In this way, supernovae served as the cosmic engines, both creating and destroying, and pushing the universe toward new phases of evolution. The explosion of the first stars did more than just enrich the universe. It also created the conditions necessary for the formation of black holes. When the most massive stars reached the end of their lives and exploded, the remnants of these stars collapsed into incredibly dense objects known as black holes. These black holes, often with masses many times that of the Sun, became key players in the evolution of galaxies. Over time, they grew larger, feeding on gas from their surroundings and eventually forming supermassive black holes at the centers of galaxies. But what role did these black holes play in the cosmic evolution? In the early stages of the universe, black holes were primarily formed by the collapse of the most massive stars. These early black holes were the seeds of the supermassive black holes found at the centers of galaxies today. As these black holes continued to grow, they influenced the formation and evolution of galaxies, driving the creation of stars and regulating the rate of star formation through their intense gravitational pull. In fact, the existence of supermassive black holes may explain the formation of the first galaxies, as they may have acted as cosmic anchors, holding the galaxies together with their immense gravitational influence. Yet, the birth of the first stars also set the stage for something even more complex, the formation of habitable planets. The heavy elements produced by these stars and their subsequent supernovae were necessary for the creation of planets. These elements, dispersed throughout the cosmos by the shock waves of supernovae, eventually found their way into gas clouds, triggering the formation of new stars. Around these stars, planets began to form, and with them, the possibility of life. It was the creation of heavier elements forged in the hearts of the first stars that made the creation of planets like Earth possible. The formation of planets, however, was not an immediate process. Once the gas clouds were enriched with the elements from supernovae, the next step was the accretion of gas and dust particles into solid bodies. This process, known as planetesimal formation, was influenced by the gravitational pull of surrounding stars and dark matter. The dense regions of gas began to collapse, creating solid objects that would eventually become planets, moons, and asteroids. The heavy elements left behind by the first stars were crucial in this process, providing the necessary ingredients for the formation of rocky planets. It was not just the death of these stars that set the stage for life. It was their role in influencing the environment. These early stars acted as the ultimate creators of the conditions that allowed galaxies to form, stars to burn, and planets to form in stable orbits around their stars. Without the death of the first stars and the supernova explosions that followed, the universe would have remained a barren place, unable to support complex structures. One of the fascinating aspects of studying the first stars is how their legacy continues to shape the universe today. The supernovae of these ancient stars not only provided the building blocks for new generations of stars and planets, but also laid the groundwork for the very fabric of the cosmos. The distribution of matter in the universe today, whether in the form of galaxies, stars, or planets, is a direct result of the processes initiated by these first stellar explosions. The influence of the first stars is also evident in the cosmic structures we observe. The large-scale structure of the universe, made up of galaxies and galaxy clusters connected by vast filaments of dark matter, was shaped by the gravitational pull of dark matter and the energy released by the supernovae. These early stars helped to seed the formation of the first galaxies, and the supermassive black holes at the centers of many of these galaxies continue to play a crucial role in shaping the growth of their galaxies. But even more than their role in creating the elements and shaping cosmic structures, the first stars were responsible for something even more profound. They provided the necessary energy for the creation of life. The light, heat, and radiation they emitted during their lifetimes and explosive deaths laid the groundwork for the development of life on Earth. Without the elements created in their cores and scattered by their supernovae, planets like Earth could not have formed. Without their light, the chemical processes that led to the creation of life would not have been possible. The first stars, in a sense, were the creators of the universe we know today. Their formation marked the beginning of a new era in cosmic history, one in which the universe would begin to shine with light, heat, and energy. Their death marked the end of an era, but also the birth of something new, the beginning of the complex, interconnected universe we now observe. The first stars didn't just light the universe, they transformed it, setting the stage for everything that followed. As we continue to study these early moments in the universe's history, we are gaining new insights into the fundamental processes that led to the birth of the stars, galaxies, and planets that we see today. The death of these first stars was not just the end of an era, it was the beginning of a new phase in the evolution of the universe, a phase that continues to unfold with each new star that is born and each new planet that is formed. As we continue our journey through the early universe, one of the most intriguing aspects of the formation of the first stars is the connection between their death and the evolution of the universe itself. The first stars did not just illuminate the dark cosmos, they began a cascade of events that would ultimately shape the universe into the rich, complex structure we observe today. These stars and their violent ends sparked a chain reaction, producing the very elements necessary for planets and, eventually, life. But their influence did not stop there. The violent death throes of these first stars, particularly their supernovae, were key to the creation of some of the most fascinating and extreme cosmic phenomena we see today: black holes, neutron stars, and the rapid evolution of galaxies. When these first stars, massive and short-lived, reached the end of their life cycle, they exploded in massive supernovae, scattering the elements they had created throughout space. These explosions were among the most energetic events in the universe, releasing vast amounts of radiation and creating shock waves that reverberated across the cosmos. The remnants of these stars, what we now call stellar remnants, would go on to create some of the most extreme objects in the universe, including black holes and neutron stars. The formation of black holes, in particular, is one of the most fascinating aspects of the death of the first stars. These black holes were the progenitors of the supermassive black holes that we find at the centers of most galaxies today. The process of black hole formation begins when a massive star collapses under its own gravity at the end of its life. If the star is massive enough, it can create a singularity, a point in space where gravity is so intense that not even light can escape. The death of the first stars thus marked the birth of these strange, enigmatic objects. But the creation of black holes also had profound implications for the development of galaxies. Over time, these early black holes began to grow, feeding on the surrounding gas and matter. This process of accretion, where matter falls into the black hole, creating immense gravitational forces, could cause these black holes to grow to enormous sizes. Today, we know that most galaxies contain supermassive black holes at their centers, and these black holes are believed to have played a crucial role in the formation and evolution of galaxies. The birth of black holes, driven by the death of the first stars, thus became a key element in shaping the large-scale structure of the universe. However, while the formation of black holes and neutron stars was a key consequence of the first stars' deaths, their supernovae also led to the enrichment of the universe with the elements necessary for the formation of planets and life. These explosions spread heavy elements such as carbon, oxygen, nitrogen, and iron throughout the surrounding gas, enriching the universe with the building blocks for future generations of stars and planets. These elements, which were created in the cores of the first stars and their subsequent supernovae, would go on to play a crucial role in the formation of planets, including Earth, and in the development of life. It is in these enriched gas clouds that the next generation of stars began to form. These stars, which were born from the remnants of the first stars, were different from their predecessors. Unlike the first population 3 stars, which were made primarily of hydrogen and helium, the next generation of stars contained heavier elements, which allowed them to cool and form more stable structures. These stars were also smaller and longer-lived, and their creation marked the beginning of a new era in the universe, one in which planets, solar systems, and even life could emerge. The process of stellar nucleosynthesis, the creation of elements through nuclear fusion, didn't stop with the death of the first stars. As these stars died, they enriched the universe with the elements necessary for the formation of planets and, eventually, life. These elements, carbon, oxygen, and iron, would form the basis of everything we know, from the rocks beneath our feet to the air we breathe. The first stars, through their death and subsequent enrichment of the universe, set the stage for the creation of planets, the formation of solar systems, and the development of life. Yet, the universe did not immediately transform into the hospitable place we now inhabit. While the death of the first stars seeded the universe with the necessary elements for planet formation, the conditions for life to emerge were far from ideal. The radiation from these early stars and their supernovae would have been intense, and the surrounding environments hostile to life as we know it. It took billions of years for the first habitable planets to form as the universe continued to evolve, cooled by the expansion of space and the accumulation of heavier elements from successive generations of stars. But as the first generation of stars gave way to the next, a gradual but profound transformation was underway. New stars, smaller and more stable, formed from the enriched gas clouds, and planets began to coalesce around them. The cycle of starbirth, death, and rebirth continued, each generation of stars creating the conditions for the next. With each passing generation, the universe became more complex, more enriched, and more conducive to the formation of planets and life. The death of the first stars, though violent and destructive, was a necessary step in this process. One of the most fascinating aspects of this cosmic evolution is how the death of the first stars directly impacted the formation of galaxies. Galaxies are not just collections of stars, they are dynamic systems, each with a complex structure and history. The first galaxies were formed from the remnants of the first stars, which had enriched the surrounding gas with heavy elements. These early galaxies were smaller and more chaotic, with stars and gas swirling together in turbulent motions. Over time, these early galaxies merged and grew, influenced by the gravitational pull of dark matter and the presence of supermassive black holes at their centers. As the universe continued to evolve, galaxies grew larger and more complex, eventually forming the structures we see today. The death of the first stars played a critical role in this process, as their supernovae triggered the formation of new stars, galaxies, and black holes. These events laid the foundation for the universe's large-scale structure, from the clusters of galaxies that we observe to the intricate cosmic web of filaments and voids. The birth and death of the first stars were not isolated events. They were part of a larger ongoing cycle of cosmic evolution. The elements created in these early stars would go on to form new generations of stars and planets, each generation more complex and varied than the last. The death of these first stars set in motion the processes that would eventually lead to the formation of the galaxies, solar systems, and life itself. In many ways, the universe was born from the ashes of these first stars, as they provided the raw materials and conditions for the universe to evolve into what we observe today. As we continue to study the universe's early history, we are gaining deeper insights into how the first stars shaped the cosmos and set the stage for everything that followed. The strange secret that the universe has been hiding all this time, the role of these early stars in shaping the very elements and structures that make up the universe, has profound implications for our understanding of cosmic evolution. These first stars were the foundation for everything that came after them, the galaxies, the planets, and ultimately, the life that arose on Earth. As we examine the role of the first stars in shaping the cosmos, one of the most profound revelations is how their explosive deaths through supernovae kick-started the creation of the elements necessary for life and the formation of complex structures. But the influence of these early stars didn't stop at the creation of heavy elements. Their explosive deaths had far-reaching effects on the very fabric of the universe, driving cosmic evolution and laying the foundation for the universe's large-scale structure. The legacy of the first stars continues to shape the universe in ways we are only beginning to comprehend. One of the most significant consequences of the first stars' deaths was the creation of cosmic supernova remnants. These remnants are the residual materials left behind after a star explodes. The remnants, which consist of heavy elements and gas, were scattered throughout space by the shock waves of the supernova. These elements, such as carbon, oxygen, nitrogen, and iron, became the building blocks for future generations of stars, planets, and galaxies. Without these supernova remnants, the universe would have remained devoid of the elements necessary to form complex structures, such as rocky planets and life. Supernovae not only enriched the universe with heavy elements, but also played a crucial role in shaping the environment in which new stars and galaxies would form. The shock waves from supernovae acted as cosmic stirrers, stirring up the surrounding gas and creating regions of higher density. These dense regions of gas, now enriched with heavier elements, became the birthplaces of new stars. The death of the first stars, therefore, did not just end their existence, it set in motion the process of stellar rebirth, leading to the creation of new cosmic structures. One of the most profound outcomes of this process is the formation of the first galaxies. The remnants of the first stars, enriched with heavy elements, helped to trigger the formation of the first galaxy clusters. These early galaxies were smaller and less structured than the large spiral galaxies we see today, but they were the seeds of the galaxies that would eventually dominate the universe. The formation of galaxies, driven by the elements created by the death of the first stars, marked the beginning of a new era in the universe's evolution, a time when stars, galaxies, and other complex structures began to take shape and interact in ways that would lay the foundation for the universe we observe today. As these early galaxies began to grow, the process of star formation continued to evolve. New stars, born from the enriched gas clouds left behind by the first stars, were different from their predecessors. These second-generation stars contained heavier elements, which allowed them to form more stable structures. Unlike the first stars, which were composed primarily of hydrogen and helium, these newer stars were made from a mixture of hydrogen, helium, and the heavier elements produced by supernovae. These stars were smaller and longer-lived than the first stars, and their formation marked the transition from the chaotic star birth process of the first stars to the more stable stellar environments that would eventually give rise to solar systems, planets, and life. In addition to the formation of galaxies, the death of the first stars also played a crucial role in the creation of black holes. The supernovae of these early stars produced black holes, which are regions of space where gravity is so strong that not even light can escape. These black holes became the centers of galaxies, and their gravitational pull influenced the formation and evolution of stars within the galaxy. Over time, these supermassive black holes grew, feeding on surrounding gas and stars, and played a critical role in shaping the dynamics of galaxies. Their influence is not just limited to galaxies themselves, but extends to the growth of large-scale cosmic structures. The formation of black holes also set the stage for the creation of quasars, bright, energetic objects powered by the accretion of matter around supermassive black holes. Quasars are some of the most energetic and distant objects in the universe, and their formation is directly tied to the death of the first stars and the birth of black holes. The first stars, through their supernovae, enriched the universe with the elements necessary for the formation of these massive black holes, which would go on to power quasars and influence the evolution of galaxies. These early black holes and quasars had a profound effect on the evolution of the universe. As black holes grew, they pulled in gas and stars, shaping the growth of galaxies and galaxy clusters. The radiation from quasars also affected the surrounding gas, influencing the formation of new stars and the growth of galaxies. The birth of black holes and quasars, driven by the death of the first stars, created the conditions for the universe's large-scale structure to evolve and for the formation of the galaxies, stars, and planetary systems we observe today. The death of the first stars and the formation of black holes, galaxies, and quasars also had a lasting impact on the universe's expansion. The radiation and shock waves from supernovae played a critical role in the process of reionization, which is the period in the universe's history when the first stars and galaxies ionized the surrounding gas, allowing light to travel freely through space. Reionization marked the end of the cosmic dark ages and the beginning of a new era of light and structure. The processes that began with the death of the first stars set in motion the universe's expansion, providing the conditions necessary for the formation of galaxies, stars, and planets. As we reflect on the legacy of the first stars, it's clear that their impact is felt across the universe. From the creation of heavy elements in black holes to the formation of galaxies and the expansion of the universe itself, the first stars were the catalysts for the complex, dynamic cosmos we observe today. Their death and the subsequent birth of new cosmic structures set the stage for the universe's evolution, and their influence continues to shape the universe we see around us. Yet, despite the immense importance of these early stars, many mysteries still remain. How did these first stars form in the first place? What conditions were required for them to ignite and burn so intensely? And what exactly happened during their explosive deaths that led to the creation of black holes and the enrichment of the universe? These are questions that continue to drive research in astrophysics and cosmology, as scientists seek to uncover the secrets of the early universe and understand the fundamental processes that shape the cosmos. The death of the first stars was not an end. It was the beginning of the universe as we know it. The elements they created, the black holes they formed, and the galaxies they gave birth to laid the foundation for everything that followed. As we continue to study these stars and their legacy, we are gaining new insights into the fundamental processes that have shaped the evolution of the universe and the conditions that led to the formation of planets and life. As we reach the final chapter in our exploration of the first stars and their profound impact on the universe, we are left with a deep sense of wonder about the intricate processes that led to the creation of everything we know. These first stars were not merely the sources of light in the early universe, but rather the catalysts for a cosmic evolution that would eventually result in galaxies, planets, and life itself. Their death through supernova explosions created the conditions for the universe to evolve from a barren expanse of hydrogen and helium into the complex, vibrant cosmos we observe today. But the death of the first stars is not just a historical event, it is a cornerstone of our understanding of the universe's future. These early stars set in motion a series of cosmic events that would continue to unfold over billions of years. As their explosions scattered heavy elements into the universe, they paved the way for the formation of new stars, galaxies, and planetary systems. These stars were the ultimate progenitors of the universe's richness, transforming the simple primordial gas of the early universe into the diverse and dynamic structures we observe today. One of the most profound aspects of the death of the first stars is the role they played in the formation of black holes. The most massive stars, when they exploded, collapsed into black holes, regions of space with gravitational fields so strong that not even light could escape. These black holes, born from the death of the first stars, became central to the formation and evolution of galaxies. Over time, these black holes grew by consuming surrounding gas and stars, eventually becoming the supermassive black holes found at the centers of most galaxies today. In many ways, black holes are the silent architects of the cosmos, shaping the growth and behavior of galaxies, stars, and other cosmic structures. The formation of supermassive black holes is not just an isolated event. It is part of a broader pattern in the universe's evolution. The early black holes formed by the first stars were the seeds of larger black holes that would grow over billions of years. As these black holes grew, they began to influence the galaxies around them, regulating the formation of new stars and shaping the overall structure of their galaxies. This process continues today, as supermassive black holes continue to exert their gravitational influence on the galaxies that surround them. In addition to black holes, the death of the first stars also led to the creation of neutron stars. These stars, which are the remnants of stars with a mass between that of a white dwarf and a black hole, are incredibly dense and have extreme gravitational fields. Neutron stars are often the sites of some of the most violent cosmic phenomena, including gamma-ray bursts and gravitational waves. The discovery of gravitational waves, in particular, has opened up new avenues of research into the behavior of neutron stars and the nature of space-time itself. These neutron stars, born from the death of the first stars, continue to serve as cosmic laboratories, offering insights into the extreme conditions that govern the universe. The death of the first stars also contributed to the process of reionization, which marked the end of the cosmic dark ages. As the first stars ignited, they emitted radiation that ionized the surrounding gas, allowing light to travel freely through space. This process of reionization had profound implications for the universe, as it allowed galaxies to begin forming and expanding and set the stage for the creation of solar systems and planets. The radiation from these stars also helped shape the large-scale structure of the universe, influencing the formation of galaxies and the cosmic web of dark matter that binds them together. One of the most exciting aspects of studying the death of the first stars is how it connects to the ongoing process of galaxy formation. As the first stars died and scattered their elements across the universe, new generations of stars began to form from the enriched gas clouds left behind. These second-generation stars, formed from gas enriched with the heavy elements created by the first stars, were crucial in the formation of galaxies. They were smaller, cooler, and longer-lived than the first stars, and their birth marked the beginning of the era in which more complex galaxies and cosmic structures would emerge. Over time, these new stars began to form in dense clusters, creating the first galaxies. These early galaxies were small and irregular, shaped by the gravitational pull of dark matter and the remnants of the first stars. As these galaxies merged and interacted, they grew larger and more structured, eventually becoming the spiral and elliptical galaxies we see today. The influence of dark matter, which was concentrated in massive halos around these galaxies, played a crucial role in their growth and evolution. Without dark matter, the formation of galaxies would have been much more difficult, as it provided the gravitational pull necessary to hold galaxies together and trigger the formation of stars. As we continue to study the first stars and their death throes, we gain valuable insights into the fundamental processes that shaped the universe. These early stars were not just the first sources of light, they were the creators of the complex, interconnected universe we observe today. The elements they produced, the black holes they formed, and the galaxies they helped create have left an indelible mark on the cosmos. Without these first stars, the universe would have remained a barren, lifeless place, devoid of the complexity and richness that we now take for granted. But the death of these first stars also holds profound implications for our understanding of the universe's future. The supernovae that marked the end of these stars' lives set in motion a series of events that continue to shape the universe's evolution. The birth of new stars, the formation of galaxies, and the creation of black holes all began with the death of these first stars. And as the universe continues to evolve, we will likely see new generations of stars and galaxies emerge from the remnants of the first stars, continuing the cycle of cosmic rebirth. In many ways, the death of the first stars marked the beginning of the universe's transformation from a hot, chaotic environment to the rich, structured cosmos we see today. These early stars were the first step in a long journey that continues to this day, as the universe continues to evolve and change. The legacy of the first stars is written into the very fabric of the cosmos, influencing everything from the formation of galaxies to the creation of life. As we continue to study the universe's early moments, we will no doubt uncover even more secrets about the role of these stars in shaping the cosmos and the forces that govern its evolution.